Okay. So first thing we're gonna do is look at how areas work. And what I'm gonna do for that is I'm gonna draw some parts out. Um, First off, let's look at triangle. I'm gonna rotate this triangle, so I'm gonna redraw it. So we're gonna draw it with AC down here. And we're gonna have D over here and B over here. Okay. For now, we're going to have this. This is x, this is 2x. So one thing we actually know is that, let's draw the height, and I'm going to call this height hx, okay? So we know that the area of ADB is equal to, well, x half x hx. And then we also know that the area of CDB is equal to half 2x hx. So what that actually gives us is that the ratio of the two areas, so ADB to CDB, is equal to the ratio of the bases, so AD over CD. Since the height is common, and that ends up being 1/2. So now what we know is that AD is 1/2 of, the area of triangle ADB is 1/2 of the area of triangle CDB. And so from that, we know since the total area is 360, we know that the area of triangle ADB is 1/3 of 360, right, which is 120. And the other one is 240. CDB. 2/3 of 360, which is 240. Okay. So now we're going to break it up further. We're going to look at DAB. Okay, and this is E. Okay, so M and M. So if we use a similar concept, what we realize is this area is equal to the area shaded in green. So as a result, we have some further breakdown, which is halving the triangle ADB. So triangle ABE has an area of, so half of 120, which is 60, and then triangle ADE has an area of half times 120, which is 60 as well. So right now, what we have is, I'm gonna erase those. So what we have is this is 60, this is 60. We're going to break this over here. Okay. So now let's get into more stuff. So according to this, so I am gonna let's look at triangle E, A, and C, and here we go, D. So this is 60. So remembering that AD over DC is equal to 1/2. We know that this triangle is equal to 120, so this is 120. This is X, and this ought to be 120 minus X because the sum of all the areas needs to be 360. Okay, so now we have this. Now let's try to use our area ratios to get a system of equations. So first off, I think we can look at, I guess, let's think. So we can look at EF over AF, right? And we know that that is equal to since there's a common height, that's equal to x over 60, right, based on triangle ABF. And based on triangle, so that's, I'm gonna like draw these out, outline them. Okay, this is one, and the other one is right here. Okay, so this one's blue, and this one is green. Triangle AFC. Okay. So this one would be 180 on the bottom. Yeah. This would be a E actually, because we're just looking at the side, sorry. So 180 and this one would be 120 minus x. So now we have a proportion, right? And now it's simple algebra. So you cross multiply, you get 180x is equal to what is it, 7200 minus 60x. So it's 240x is equal to 7200, x is equal to 30. They're asking for the area of EBF, and that's what we're looking for, x, so it's 30. So this is just using the area ratios, and that's really important. I find that one of the nicest ways to find ratios. Again, if you didn't understand this entire solution, it is a little difficult, but the biggest thing I would take away from this is that the height and bases play a role. Like half BH formula is very, very powerful, and area ratios can be really useful in that sense. Again, this is a question 24 from a recent year, so you wouldn't be totally expected to do it, but this idea could be applied to other problems. Okay, next question. So a square with area 4 is inscribed within a square with area 5 with each vertex of a smaller square on a side of the larger square. A vertex of the smaller square divides a side of the larger square into two segments, one of length A and one of length B. So this is B and this is A. What is the value of AB? So I'll give you some time to think about it and work on it, and then we'll come back and discuss the question.